Yet again, educator Carlos Plain of Durham School states conclusively, "I went through my whole time on Earth engaging with a particular theory of the universe. Likewise, at last, the speculation is being endeavored. I invite that, since that is the way we push ahead, that is the way we gain ground in science." The James Webb Space Telescope is disrupting a complex plan of what has been viewed as truth in cosmology. For the new year, another ultra-deep image shows that we have serious goofs in cosmology. The telescope that was meant to show us the first stars of the universe is transforming into a challenge to past perspectives and may present us with a completely new science. Not all specialists are reeling in fear at these new realities. Other informed authorities welcome the advancements, since it has long been evident that something was wrong with our old theories. The deviation in the study of the expansion speed of the universe alone should have shaken experts' perceptions long ago. Yet they adhered to old theories. The vast cosmic microwave background radiation, CMB, considered the oldest light in the universe, was created around 380,000 years after the Big Bang, when the universe had cooled enough for electrons and protons to form stable hydrogen atoms. Researchers call this process reionization, which made the universe transparent to light. The CMB was first observed in 1964 by American physicists Arno Penzias and Robert Wilson while they were working on a new type of radio antenna technology. This discovery was, for a long time, seen as perhaps the strongest evidence for the Big Bang theory, earning Penzias and Wilson a Nobel Prize and a prominent place in the history of cosmology. The CMB offers a view of the early universe, with small temperature differences providing critical data about the conditions shortly after the Big Bang. Scientists used the CMB as a strong baseline to evaluate key measurements of the universe's composition, including its expansion rate. The cosmologist Edwin Hubble had already established in the late 1920s that distant galaxies recede from us at speeds proportional to their distance. Today, these observations are known as the Hubble law or the Hubble constant. Hubble, however, lacked the advanced measurement methods available decades later, when the CMB was discovered. These methods recalculated the expansion rate at values generally lower than Hubble's original estimate. Later, scientists recalculated the rate using Type Ia supernovae as standard candles, providing consistent light that could serve as reliable measuring points. Estimates from the CMB yielded an expansion speed of about 67 km per second per megaparsec, while those using supernovae yielded about 74 km per second per megaparsec. What does this discrepancy in determining the universe's expansion speed really tell us? Did you know that this inconsistency has been known since the 1990s? Since then, experts have suspected that something might be wrong with the evaluation of the CMB, the assessment methods, or the concept of the universe's expansion. The anomaly between the observed and expected values of the expansion rate is referred to in science as the Hubble tension or SAA tension. The implications of this tension are vast, indicating that fundamental aspects of how we understand the universe may be flawed. For decades, experts were perplexed. Since the James Webb Space Telescope became operational, it has provided astonishing data that might finally shed light on the issue of the universe's expansion speed. It has revealed systems so old and mature that their formation must have hypothetically begun before the Big Bang, overturning old cosmological theories. Scientists no longer speak of mistakes or evaluation discrepancies. They discuss the greatest crisis in modern astronomy. Not only might the expansion rate be incorrect, but the entire concept of the Big Bang itself is being called into question. Images from the telescope provide evidence of a universe completely different from what we long believed. The Hubble tension was the first blow to experts who still believed in old theories. Now they face a dilemma. Do we truly understand the universe? Various researchers stand amidst the ruins of their once pristine fountain of both discovery and frustration, analyzing space with fear and wrestling with doubt. The discoveries made possible by the James Webb Space Telescope, JWST, are not merely small adjustments to our understanding of the cosmos. They are revolutionary. They suggest that the early universe may have hosted fully formed galaxies far earlier than the Big Bang theory would allow. This finding undermines core assumptions about the universe's timeline, star formation, and the gradual buildup of cosmic structures. Critics of traditional cosmology now question the validity of long-held concepts such as dark energy and dark matter, foundational elements of the lambda CDM model. These invisible forces, used to explain the observed expansion and structure of the universe, may need to be redefined, or replaced entirely. Such shifts, though alarming, could pave the way for groundbreaking discoveries and a deeper understanding of the cosmos. Moreover, new evidence has sparked debates about the concept of universal homogeneity, the assumption that the universe looks roughly the same in every direction on a large scale. The discovery of ancient, massive galaxies clustered together in ways that defy predictions suggests that the universe might be more varied and chaotic than previously imagined. Scientists now face a daunting challenge: adapting their methods, tools, and theories to account for these unexpected findings. Some are embracing these challenges, seeing them as opportunities to innovate and expand the boundaries of knowledge. Others are more cautious, hesitant to abandon the familiar frameworks that have guided decades of research. Despite the uncertainties, one thing is clear: we are entering a new era of cosmology. The James Webb Space Telescope has opened a window into the unknown, forcing us to confront the limits of our understanding and consider possibilities we once deemed improbable. As Carlos Plain eloquently stated, "I invite this upheaval because it is the way we push forward. It is the way we make progress, not only in science but in our broader quest to understand our place in the universe." The coming years will likely see more groundbreaking discoveries, further refining or dismantling our current theories. Whether it means rewriting the story of the cosmos or uncovering entirely new chapters, the future of astronomy promises to be as thrilling as it is uncertain. With what they find, considering the crisis in science, we ought to ask ourselves, what do we genuinely have some familiarity with the universe? To answer this, we really want to comprehend how science functions. Speculative analysts use a mind-boggling set of numerical models, cautious information, and logical reasoning to move from general to particular conclusions. Their comprehension comes from a mix of perception, qualities, fundamental outcomes, and speculative evaluations. The term hypothesis alone shows that these are constructs and ideas, not absolute pieces of information. The most significant data we have are the photos telescopes provide, the sound waves and radiation collected with radio telescopes, and the latest data from neutrino surveying systems or gravitational wave detectors. With the James Webb Space Telescope, we now have an instrument that can split light into individual frequencies and analyze it in phenomenal ways. Webb can show us the essential composition of galaxies in the early universe, more than 1 billion years ago, including how much mass they contained and the number of stars present. It can also track the shape and course of a galaxy's evolution. Webb, however, has limitations. For example, it can't always conclusively determine whether we are observing galaxies or black holes with massive gravitational pulls that emit as brightly as a galaxy. We must face the reality that our science has long accepted an excessive number of possibilities as facts while dismissing alternative explanations. Research has for decades been certain about its accuracy. The latest discoveries from the James Webb Space Telescope are crucial clues to replacing theories with new insights, as has historically happened in science. Analysts eagerly await new revelations, which are unexpectedly astonishing and diverse. Experts are striving to develop new explanations. The new discoveries shake the foundations of our current science, unsettling many professionals. The current models of modern science are still largely based on Isaac Newton's laws from the 17th century. His laws of motion and gravity were the foundation of our understanding of the reality of this world and the universe for many years. Newton's rules explain the motion of objects under normal circumstances and work exceptionally well on Earth. However, in space, his theories required improvement, which was largely accomplished by Albert Einstein in the early 20th century. Einstein's special theory of relativity, published in 1905, changed how we interpret reality, showing that space and time are relative and depend on the observer's motion. His general theory of relativity, published in 1915, extended this idea with mathematical descriptions of gravitational properties based on the curvature of spacetime by masses such as stars or galaxies. Einstein's principles and ideas were groundbreaking in various areas. However, he also understood their limits. He knew his theory could never completely describe the universe and yearned for a unified theory, which he never achieved. No other professional has reached this stage either. Wouldn't it be fascinating to know where this understanding lies? Michio Kaku, a prominent astrophysicist from the USA, said in an interview that solving this problem would undoubtedly win a Nobel Prize. Could we explore whether scientists have missed potential misinterpretations or whether our telescopes are at fault? Dark matter and dark energy are at the top of the suspect list for the fundamental causes of the cosmological crisis. Our evolving models of the universe propose that dark matter and dark energy make up around 95% of the universe. However, neither has been clearly observed, and their confirmed presence has never been demonstrated. They might not exist in any form or shape, requiring alternative explanations for the universe's expansion and the dynamics of galaxies. On the other hand, they could have properties we don't yet understand. One idea is that the actual properties of dark matter and dark energy have changed over time, possibly indicating some form of evolution. Gravity is another theory to be tested. This force, which causes attraction through mass or curvature in spacetime, has not yet been fully explained. The ideas of spacetime curvature, originating from Einstein and traditionally supported, may require revisiting. We can't dismiss the possibility that gravity has unexpected properties or that another force is responsible for the gravitational attraction between objects. Over time, a few constants have been established in astronomy and cosmology as universal principles. The study of the universe has always been a journey defined by our relentless quest for understanding and discovery. From ancient human civilizations observing the stars to modern space telescopes examining the depths of the universe, every step in development and theory has revealed new mysteries while challenging established beliefs. In the field of cosmology, the James Webb Space Telescope, JWST, remains a beacon of our scientific progress, promising to revolutionize how we interpret the universe's origins and evolution. Launched with extraordinary capabilities, JWST represents a leap forward in observational space science. The cosmic microwave background, CMB, often referred to as the glow of the Big Bang, offers a glimpse of the universe as it existed only 380,000 years after its formation. This ancient form of radiation carries critical information about the universe's early conditions, including its temperature variations, which are vital to understanding the formation of galaxies and large-scale structures. The disparity in the calculated expected values of the Hubble constant, known as the Hubble tension, has been a subject of intense debate. It suggests that something is amiss with our fundamental understanding of the universe and its origins. Discoveries challenge conventional theories and demand a reassessment of whether our perspective on cosmic evolution is fundamentally flawed. New insights might reveal hidden aspects of the universe's creation, raising questions about dark matter and dark energy, two unexplained components that make up most of reality. The advancement of science relies on the ability to reshape our theories based on new data. Webb's mission embodies this pursuit. Its discoveries will serve as a foundation for future cosmological discussions and should spark new perspectives on the universe's mysteries. The future of cosmology might witness dramatic changes, leading to significant implications for our understanding of the universe, from the Big Bang to the ongoing processes that define its fate. The solution to the great cosmic puzzle might lie beyond our current knowledge, and Webb's observations may ultimately be pivotal in uncovering new insights that could reshape how we interpret reality itself.